the things which we call it grand partition functions. You can write it the grand partition function for the system, and I want to tell you that that will be the end. So you remember the Q was an D in the grand canonical ensemble, and the D was, in this case, D is a function of Z, V, and T, is given by this equation. In Bose-Einstein case, it will be and in the Fermi dimension. This proved not so it should be a better way to derive that, but I think is, but we can't now waste the time over that. For me, it was important to know that what's the grand partition function for different systems like boson and fermion, and you understood that it comes by the calculation of the WNI, the waves of the distributing NI particle between the GI energy level. So because you have a different cell, so you need to do this calculation, counting in each cell, and finally multiply that to the whole. So that was the result. The number of the particle can be seated in each energy level EI. And from here you can find the entropy. From entropy you can get the pressure. So this is the equation. So this gives you the P, but if you want the partition function, this is the partition function which you have it here. So using the partition function, you can calculate the average of the particles. If you back to the chapter of the grand canonical, from the chapter of grand canonical, if you give me the grand partition function D, or if you give me Q, just by partial derivative, easy partial derivative, you can find that the different parameters like the pressure, like the N, like the average of the energy or something like that. So in our case, it will be like that. And this is called the mean occupation number, or the mean of the particles which have the energy. Mean occupation number. Occupation number was which is Ni, and now you do the averaging over the all possibilities, so mean occupation number is average N. So this is the mean occupation number. So, yes?
What is the difference between N and N star?
So this is the things which I told you, that when at the beginning, when you have the energy omega E and you have the omega, you always, for each energy you have a 1 omega. So if you repeated this, so it will be the Gaussian, the most probable state, or the most possibility for the system, possible way for system when the system wants to reach the equilibrium is the one which they give the maximum omega E. With maximum omega E, you can reach very quickly to the equilibrium. Each one of these volts need a very technical description actually. So this is what we do here. Instead of the energy EI, we have another parameter Ni. Ni is the number of the particles can be seated in the energy level EI. So you have some maximum or minimization over this Ni instead of the E. Because when you take a derivative, you will find the maximum or minimum of the function at the given point at the one value like x star. So this is the x star actually. This is the most probable state of the system where energy level. I want to, this is a too abstract, so I want to go on the, move to the boson systems. So the material which I was needed to start my study about bosonic system I already have. So I have a grand partition function for bosonic system. So now I want to go and study the statistic of the bosonic system. So which we call it ideal boson gas, Bose gas, Bose systems of gases. You remember we defined it a quantity very, very fast. We call it the thermal wavelength. Even in the Halliday in fundamental physics, you can find it that. This is actually in the order of the mean distance between the two particles. Mean distance between particles in gas. As I told you since last talks, we start to talk about the quantum behavior of particles, about the wave function of them, so something like that. We have the approximation here to consider the quantum effect. If you want the quantum effect to be important for you, this is the approximation to include the quantum effects. So what is the n? So n here is actually the number of the density is related to the density actually. If n under 3 is set to the 0, we will have the classical limit. So do you know why? Because this is a good parameter and a dimensionless parameter. This is very important that this parameter is dimensionless. I mean there is no dimension for that. It's not kilogram, centimeter or something like that. This is a dimension parameter. So we needed a dimension parameter always in quantum statistics and quantum mechanics to study the properties of the system. So to use the expansions or these things like that, perturbation or like that.